Today we are going to look at the Quantum Zeno effect, and for that our journey begins in ancient Greece, where a tortoise is challenging Achilles to a race. The tortoise claims that, if given a 100-meter head start, Achilles will never be able to beat it. It claims that to catch up in the first place, Achilles will have to cover half the distance, before that a quarter, an eighth, and so on. So he will have to cover an infinite number of finite distances, seemingly impossible. After all, how can such a series ever lead to a finite number? But thanks to calculus in the 16th and 17th centuries, it can be found that if the distance continually decreases and Achilles' speed increases, then he will be able to overtake the tortoise. But what has Achilles and a tortoise got to do with quantum physics? Before that, we need a little background. Firstly, each and every quantum particle, that is, a particle small enough to display quantum behavior like electrons or atoms, can be described with a wave function, which essentially describes the sum of the probabilities of finding that particle in one state or another. Second, measuring a quantum particle determines what state it ends up in. As we just mentioned, there are different probabilities of finding a particle in one state or another, therefore you're more likely to see the higher probability outcome. For example, near the beginning of a state change, a particle is much more likely to be found in its initial state than in the state it will end up in. That said, it is just a probability. There's always a small chance of it changing state. These concepts are key to understanding the Quantum Zeno effect. As measurement is an active process, it affects the state of the particle being measured. This is because before a particle is measured, it exists in a superposition of states. That is to say, is in both states that it could be in at the same time. However, once measured, something happens, which means that we only observe one state. Now, if a particle is in the process of changing from state 1 to state 2 and is in a superposition with its probability leaning towards finding it in its initial state, when it is measured, we are more likely to see it back to square one, exactly in its initial state as if you reset the particle. Which means that if you kept on measuring it, it could pretty much never change state. Pretty much because there's always a very small probability that it will be able to in the small time that elapses before a measurement is made. This effect was demonstrated at the US National Institute of Standards and Technology in 1990. A few thousand beryllium ions were exposed to microwaves to slowly make them change state. Now, when I say change state, I don't mean melting or boiling, but rather the one that occurs when an atom absorbs or emits a photon. Anyway, the first time that this change of state was performed, the whole change was allowed to take place before a measurement was taken. Under these conditions, it took 256 milliseconds for the entire change to occur. The measurement was taken by using an ultraviolet laser. The frequency of the laser meant that state 1 ions would happily absorb a photon and then re-emit it on a carefully positioned camera, whereas state 2 ions would do no such thing, and therefore the number of bright spots on the camera would indicate how many state 1 ions there were. Now, this was to be proved quite useful, because the second time that this experiment was performed, there was a measurement made halfway through. However, this time, at the end of 256 milliseconds, around half as much light was produced as was seen at the very beginning, indicating half was still in state 1. Now, why was this? Well, at 128 milliseconds, as one would expect, the particles are around halfway through their transition and so have a 50% chance of either collapsing to state 1 or state 2 once measured. Therefore, once measured, this is what happened. Half of them were observed as being in state 1, whereas the other half were observed in being in state 2. The ones in state 2 remained so to the end of the experiment. The ones in state 1, however, had to start their transition all over again and were measured back to state 1 again at the end of the experiment. Now, the frequency of their measurements was eventually increased to 64 times, at which point the chances of the ions ever converting to state 2 was less than 1%, an almost negligible amount, due to the very small probability that we discussed earlier. And this is why it's called the Quantum Zeno effect, because just as Zeno thought that Achilles would never be able to catch up to the tortoise, these particles are never able to change state as long as a measurement is made quickly enough, of course ignoring the very small chance that it does.